is to explain the ionic basis of the resting membrane potential. So we have talked about the concentration gradient and the chemical driving force, the electrical gradient, and how that is influenced by the membrane potential. And so what we're going to move on to speak about today is how do we establish that resting membrane potential? How does that come to be? And in order to do that, we're going to have to look at two ions specifically, that is sodium and potassium. We will talk about how they move independently across the cell membrane, and then we'll combine that together and talk about how they move together and they help to establish the resting membrane potential. So just to sort of jolt your memory from what we said before, we described the resting membrane potential as being -70. That was the value that we ascribed to it. But we didn't talk about how it actually came about, what ions are playing a part in that, and how we actually established that potential. So that is what we're going to do today. The resting membrane potential is very important because it is the basis for which we can excite cells like muscles and neurons. Because it's resting at -70, there is now an opportunity to excite that cell and increase that membrane potential to become more positive, which allows for ions to flow in and out of the cell. So we'll talk about how we establish it first, and then we'll go on in the next chapter, chapter 8, and talk about how we can excite cells via a process called the action potential. So we need to first describe the ions that play a part in the resting membrane potential. That would be potassium and sodium mainly. That is not to say that calcium does not also move, chloride does not also move, things like amino acids, which are charged, can also move across the membrane, but for the majority of the membrane potential, it is only influenced by the ion sodium and potassium. It exists because there are more negatively charged particles or ions inside of the cell, and there are more positively charged particles or what we would call cations on the outside of the cell. All cells have a resting membrane potential. It's going to vary depending on what type of cell. It's going to start anywhere from -5 millivolts to -100 millivolts. For neurons, which is going to be the main focus of our conversation now and as we get into the action potential, the resting membrane potential is about -70. Later on in the course, we will talk about cardiac muscle cells, which are slightly different, and they have a resting membrane potential of -90. So this can vary depending on what cell we're looking at, but for our intents and purposes, we're going to start off with neurons, and they will be starting at -70 at rest. Now, in order to determine the equilibrium potential for potassium and sodium, we need to think about two different forces, right? And so this should be a refresher or a review from what we described before. So the ion concentration gradient, which is another way of saying the chemical driving force, right? How there are different proportions of the ion across the cell membrane. We also want to think about the electrical driving force, that is influenced by the membrane permeability to these ions and then the membrane potential that we're going to end up describing. We want to think about the permeability a little bit more specifically. To describe that, when we talk about permeability, we're simply talking about how easy is it for an ion to get through the membrane. Okay, if you remember us speaking about diffusion and describing permeability relative to diffusion, it's a similar phenomenon here. How easy is it for this ion to get in and out of the membrane? And because ions are charged particles, they cannot go right through the phospholipid bilayer. They must use channels. In other words, the membrane permeability is simply a reflection of how many channels for that ion are in the membrane. Okay, really important to make that note. When we talk about the membrane permeability to sodium, for example, it's simply another way of saying, are there a lot of sodium channels in the membrane, or are there are a few sodium channels in the membrane, and that will affect the permeability of the membrane for sodium. Let's describe some of the terminology that we're going to use in order to describe how we establish this potential. So first of all, we want to think about a potential difference. And we know that a potential is just a difference in voltage, Okay, if I have a high amount of charge inside, outside the cell, and I've got a low amount of charge on the inside of the cell, automatically I have a difference in voltage, and so I have a potential. So a potential is a force that has the ability or the potential to move particles. Okay, the membrane potential. We said that this is specifically the difference across the plasma membrane. We always give this in reference to the inside of the cell, and for that reason, we describe the resting membrane potential is -70, for example. What that means is that at -70, the cell is at rest, and this also means the inside of the cell has more negative charge than the outside of the cell. So we always reference the inside of the cell when we're speaking about the membrane potential. The resting membrane potential we just described. So this is what's happening at the cell at rest. So it's not receiving any additional signals or inputs from other sources like neurons. Other neurons, can signal neurons, right? And so they can receive additional jolts or volts of energy. And so when that is not happening, we can consider the cell at rest. Some other terms that we will describe also when we move on to speak about the action potential are the graded potential. So this is a very small change in the membrane potential versus the synaptic potential. This is happening across the synapse, which is a cell-to-cell junction. The receptor potential, all right, this is produced by certain receptors that are on the membrane. They can be bound by ligands. And again, these terms will come up again and again, and we'll describe them further. And then lastly are the action potential and equilibrium potential. So the action potential is the large, rapid change in the membrane potential that is a result of exciting the cell. So you hear me talk a lot about excitable cells. When we fully excite a cell, it's going to have a rapid upshoot in the membrane potential, and that is referred to as an action potential. Lastly, the equilibrium potential is something we described before. It is the membrane potential at which there is no movement across the membrane for a specific ion because the ion is said to be at its equilibrium. That is, the chemical driving force and the electrical driving force are equal and opposite, and so the ion or the particle is at a standstill, right? Zero movement at that specific membrane potential. Right. I don't want you to necessarily memorize these, but I want you to come back to these, reference these, because we're going to be using these terms again and again, and I want you to have a reference point so that you can further define them for yourself. The ones that I think are important are going to be the resting, the action potential, and the equilibrium potential. Those we will continue to talk about as we go forward. All right, let's begin speaking about the sodium-potassium pump. So sodium-potassium pump, we looked at this on Monday. If you remember at the end of our class, we talked about a cell and we looked at all the different types of examples of transport that was happening across that cell. We talked about the sodium-potassium pump being a measure or an example of primary active transport, where sodium was being pumped out of the cell, potassium was being pumped into the cell, and so this is what we refer to as the sodium-potassium pump. 20% of the resting membrane potential is directly a result of this pump. So this pump is pumping 3 sodiums out for 2 sodiums in, and so there's a net positive charge leaving the cell because both sodium and potassium are positively charged. And so if we have more of it going out, more of that positive charge going out than we have coming back in, we have a net positive charge leaving the cell. And so when we think about this -70 value, 20% of that is coming from the action of this pump, which is causing more positive charge to leave the cell, and so more negative charge remains behind inside the cell. Now, 80% of that resting membrane potential is going to be indirectly due to this pump as well. So thinking back to our pump, it's pumping 3 sodium out, 2 potassium in. What ends up happening is we now have more sodium on the outside of the cell because of this pump, which means that sodium is at a lower concentration inside. What do we have there? We now have a concentration gradient. Likewise, we have potassium at a lower concentration outside the cell and a higher concentration inside the cell. And so now we see, again, a concentration gradient for potassium. So the concentration gradient favors potassium moving from high to low concentration. So it's going to move inside the cell. And then it's also going to have the concentration gradient for potassium will be in the opposite direction from inside the cell to outside the cell. All right. So I say all of this to say that 20% of the resting membrane potential directly comes from the movement of the sodium-potassium pump, whereas 80% of that resting membrane value, which is -70, indirectly comes from this pump because it now creates concentration gradients, which favors the ions moving in different directions. All right. Now, a typical neuron is going to be more permeable to potassium than sodium, and it's specifically going to be 25 times more permeable to potassium. Thinking back to what we said before, we said the permeability was a reflection of the number of ion channels. So what can we say about the number of potassium channels versus the number of sodium channels? Who can think about what this means relative to the number of channels? If we say that potassium is 25 times more permeable than sodium, what does this mean relative to the number of channels?
Is it more negative or?
Okay, yep, so it's going to be not necessarily more negative. It's going to be 25 times more of what? If the channels are a reflection of the permeability, it's going to be 25 times more channels, right? So when we say that the cell has a higher permeability for potassium, we're simply saying that the cell has 25 times more channels or doors, so to speak, for potassium to move through. And so it has 25 times less of those channels or doors for sodium. In other words, more potassium, can move through the cell more easily because it has more opportunities, it has more channels, and so the cell is more permeable to potassium. We also want to think about the ion distribution of these across the cell. So on the outside of the cell, we have lots of sodium. All right, think back to our sodium-potassium pump, pumping more sodium out. So now on the outside of our channel, we have more sodium, and sodium is going to be opposed or balanced by chloride. Sodium is positively charged, chloride is negatively charged. They're going to oppose each other and balance the outside of the cell. On the inside of the cell, we have potassium, and that is going to be opposed or balanced by organic anions. So organic anions are typically inside the cell, they're negatively charged, and so they're going to help to balance out the excess potassium that's found on the inside of the cell. Okay, so those two points that we mentioned on the previous slide there are going to be important, so keep those in mind as we continue to build the story. So what we'll do here is we're going to describe a hypothetical cell that's moving only potassium, right? And I kind of want to explain the big picture of what we're doing, and then we'll get into the details, and then we'll kind of go back to the big picture so that we can help this make more sense. So we think about a cell as having or as allowing the movement of both sodium and potassium together. So what we're going to do is we're going to separate those two ions. We're going to look at potassium exclusively, think about a hypothetical cell, because we know that our cells don't actually only move potassium, but in order to better study the movement of potassium, we're going to isolate potassium and talk about a hypothetical cell only permeable to potassium. We will do the same for sodium. We'll talk about a hypothetical cell that is only permeable for sodium in order to better study the movement of sodium. And then at the end, we're going to put those two scenarios together and talk about an ideal cell in our body and how the movement of both sodium and potassium together end up giving us that -70 millivolts, which is our resting membrane potential. So starting out with this cell only permeable to potassium, what we see is the chemical driving force is out of the cell. Remember, we have our sodium-potassium pump, so always think about that in the back of your mind. It's on the membrane of our cells, specifically that basolateral membrane that we talked about on Monday, and it is pumping more potassium into the cell. So as we can see here, we have lots of potassium on the inside of the cell, fewer numbers of potassium on the outside of the cell. So automatically, we now have a concentration gradient out of the cell. In other words, a chemical driving force out of the cell. All right, so that's part one. Part two is we now bring in the second force that we know is acting on potassium, which is the electrical force. So as potassium begins to leave the force by way of its chemical driving force, guess what? It leaves behind unopposed negative charge. Remember, we talked about potassium being balanced out, right? If you go back here, on the inside of the cell, potassium is being balanced out by these negatively charged anions, right? These organic anions that are inside the cell. So if more potassium starts leaving the cell, we have an excess negative charge remaining behind. And so as potassium starts to move, according to its chemical driving force, we have more negative charge left on the inside of the cell. Now we can begin to think about our electrical force, because our electrical force wants to pull potassium back towards the negative charge. If you remember us describing, the negative charged environment is where a positively charged ion would like to be. That's the positive attracts negative that is responsible for the electrical force. So as we see potassium leaving the cell because of the chemical force, we also see potassium being pulled back into the cell because we now have a negative environment. And so it's going to honor the electrical force that wants to pull it back on the inside of the cell. All right. And so we talk about what happens when we want to think about the overall movement of an ion. We simply combine those two forces. So we add the chemical force, which is moving out of the cell, to the electrical force, which is moving into the cell. And because they are moving in opposite directions, we simply subtract the larger force from the smaller force, and then the larger force will be the direction of the overall movement. All right. So eventually, based upon those two movements, we now approach equilibrium. So potassium's equilibrium is -94, right? That's a set value for potassium that never changes. And so when the cell gets to -94 millivolts, potassium is at equilibrium and it is no longer moving because the chemical force is equal and opposite to the electrical force, and the magnitude of movement is 0, and they're in opposing directions. Okay. So let's sum up what we have said so far. We said that an ion is at equilibrium when there is no net force or no net movement across the membrane. Another way to express that is that the chemical force and the electrical force are in equal and opposite directions. And so the electrochemical force is 0, and so there is no net movement of that ion. Okay. Let's move on to speak about the exact same forces that are acting on sodium. So once again, we're going to take a hypothetical cell only permeable to sodium and talk about the relative distribution of sodium, and talk about how the chemical force and the electrical force are acting on sodium. So in order to do that again, we're going to recall this distribution that we mentioned earlier. On the outside of the cell, we have excess sodium balanced or opposed by chloride. On the inside of the cell, we have excess potassium balanced or opposed by organic anions. Okay, so let's start off just the same way that we did for potassium. Let's start off in the same fashion here for sodium by looking at the sodium-potassium pump, which is pumping more sodium out of the cell. Although it's not shown here, we want to think about it always being on the cell membrane, pumping more sodium out. And so now we have an excess of sodium on the outside of the cell, right? And so the chemical driving force for sodium is going to be from high concentration to low concentration, which is going to be into the cell. Okay. Now, as sodium begins to move, as sodium starts to diffuse into the cell according to that concentration gradient or that chemical force, guess what? It leaves behind more positive charge. Okay, the inside of the cell is going to become less negative as more of that positive charge floods to the inside of the cell. And now we have an electrical force that is pulling it in the opposite direction. Remember, there's more sodium out here. It's positively charged, but it's being balanced by chloride. As more of that sodium moves into the cell, we see more negative on the outside and more positive on the inside because more of that positive charge rushes in. Now we can bring into play the electrical force. So now because we have positive inside, negative outside, the electrical force wants to pull a positively charged ion like sodium into the negative environment, which happens to be on the outside of the cell. So what we see here initially, right, because this is going to change, is that the chemical force is inside, the electrical force is on the outside, and the cell begins to continue moving the ions in these two general directions. Now, the cell eventually is going to approach its own equilibrium for this ion. And again, the equilibrium potential for sodium is a set value of positive 60 millivolts. Just to reiterate what that means, at positive 60, the cell is no longer moving sodium. The electrical force is exactly equal and opposite to the chemical force, and there is zero ECDF or zero net movement for sodium. Okay. So just to recap the movement of sodium, there are two forces acting on it, a chemical trying to move it in according to that concentration gradient, and then an electrical trying to move it out. But initially, guess what? There's a stronger chemical force. And so the stronger chemical force continues to move, but the electrical force will continue to increase. And eventually, we're going to see that for sodium, the electrical force is also going to be moving onto the inside of the cell. Okay, when we add potassium's movement into the picture, we're going to see that the direction of movement for sodium, both of those values will be into the cell. Okay, so let's combine both ions at this point and look at the combined forces together. So this is just a different way to look at everything we have said so far. Now we're taking both of the ions into account and talking about their chemical forces together and then their electrical forces together. So thinking about the chemical driving force for potassium, it's going to be out of the cell. For sodium, it's going to be into the cell. And this is based exclusively on the concentration gradient. So we know that there's excess sodium outside, excess potassium inside. So sodium wants to get in and potassium wants to get out, right, according to those gradients. Now, if we think about the membrane being more permeable to potassium, that's going to have a big part to play in how we end up at a membrane potential that looks more closely or closely resembles the equilibrium potential of potassium, simply because the cell is more permeable to potassium. And if you remember what we described earlier, all that means is that there are more doors, there are more channels for potassium than there are for sodium. And so there are more opportunities for potassium to leave than there are for sodium to come in. In other words, more potassium can leave the cell than sodium can enter because the cell is 25 times more permeable to potassium than it is for sodium. So guess what starts happening? Even though we have those concentration gradients, right? Even though we have those concentration gradients, the permeability is a limiting factor. It doesn't matter how strong the gradients are. If there are more doors, if there are more channels, that is going to more greatly influence how much of the ion can leave or enter the cell. So more potassium is able to leave the cell than sodium can get in. Okay, I see a hand raised. I'm going to pause here.
if this was out of balance, how would that affect the body?
So this is a really good question, and this kind of will help us establish the scope of where we are. So these are hypothetical scenarios, right? So we're thinking about how we establish the resting membrane potential. And so these are basically dividing these two ions, talking about how they move independently, and then talking about how they move together to influence the cell. So in actuality, in our physiology, we don't ever see sodium moving exclusively or potassium moving exclusively, right? That's just a hypothetical scenario that we're using to describe how these ions move independently. In our physiology, in actuality, all of these ions are moving together. And that's kind of the end goal that we're going to end up describing when we put all of these forces together. Okay, so that's a really good question, and we're kind of building the story of how we get to that negative 70. Which ions are moving? What's the permeability difference for us to end up seeing a negative 70 value when the cell is at rest? All right. I hope that answers that question a little bit. Okay. If not, please go ahead, drop follow-up questions in the chat. So we said that more potassium leaves the cell than sodium can come in. And so we start to see a negative 70 or a negative environment inside the cell because of this difference in permeability. Okay, now we're going to think about the electrical force. Remember, the electrical force obeys the difference in charge. So now that we have established a difference in charge, right, now we see more positive outside and more negative outside. Now we can introduce the electrical force into the equation. So the electrical force for sodium is going to be into the cell, right? So remember, sodium is positively charged. The inside of the cell is negatively charged. So sodium wants to get to this negative area. And if you remember our previous discussion, that it also has a chemical force, which is into the cell. So if we think about the movement of sodium, if we combine these two forces, sodium has a really strong electrochemical driving force that favors it wanting to get into the cell. Because we're going to combine the values of both of these forces, add them together, that's going to give us a bigger value, and a combined overall direction, because they're both moving in the same direction, will be into the cell. If we do the same for potassium, potassium has forces acting in the opposite direction. So it has a chemical driving force, which is favoring its concentration gradient that wants it to move out of the cell. And then it has an electrical force because potassium is a positively charged ion. It's going to want to get into this negatively charged area here, just like sodium. So what we will see is that both of these ions want to get inside the cell according to the electrical forces. And so potassium will also want to move into the cell. Now, likewise, we're going to combine these two forces. And we talked about what we do when the forces are acting in opposite directions. We simply subtract the smaller force, which happens to be the electrical force, from the bigger force, which happens to be the chemical force. The overall direction will be in the favor of the bigger force, which is the chemical force, and the value here is going to be smaller. Why will the value be smaller? Because we had to subtract, because we had two opposing directions. So we had a large force moving it out and a smaller force moving it in. So we subtract the smaller force from the bigger force, which gives us a smaller value, but the overall direction being in the direction of the bigger force, which is out. All right. So just combining these two things, we now have an electrochemical driving force for potassium that wants to move it out of the cell, but it's going to be a smaller magnitude. It's not going to be the great strength or the large magnitude that wants to move sodium, simply because sodium's forces are moving in the same direction. So we combine them, which gives us a bigger magnitude, whereas potassium's forces are acting in opposite direction, so we subtract one from the other, which gives us a weaker or smaller magnitude. Okay, now we kind of put all the pieces of the puzzle together. The electrical force, the chemical force, the movement of sodium independently, the movement of potassium independently, and the difference in permeability, the fact that we have three more channels, right? This is illustrated as 3, but earlier we said that it's actually 25 times more. So there's a larger permeability for potassium to move out, but it has a weaker force, whereas there is a smaller permeability for sodium to move in, but sodium has a stronger force. Okay, so now when we think about combining all of those different moving parts and the cell starts to continually flux these ions, and then it's going to approach what we call a steady state where there is no more net movement. So we still have ion movement, sodium, potassium pumping sodium out, and then this channel moving sodium in. Same way we have the sodium potassium pumping potassium in, and then these channels sort of leaking sodium out. So if you remember us speaking about the pump leak system, so the sodium potassium pump, which is 20% of that resting membrane potential, and in conjunction with the leak channels, which gives us 80% of that resting membrane potential, we're pretty much putting all those things together. And when this system approaches steady state, we see a membrane potential of negative 70 millivolts, and that is how we establish our resting membrane potential. So if you were to take any of our neurons and you were to put a voltmeter into that neuron when it is at rest, the inside of that cell has negative 70 more charge than the outside of the cell because of all the various factors that we just described.